Okay, the next one is exercise 6. Actually it has 4 parts, but let us first solve this one itself. We have to prove that every integer of the form n to the power 4 plus 4 is composite, where n is a positive integer greater than 1. Okay, and you can of course see that if you take n equal to 1, then this integer becomes 5, which is prime. Okay, so that case has been discarded by assuming that n is greater than 1. And there is a hint actually also. The hint is just simply this, that we have to write this as a product of two quadratic factors, and that's what we are going to do. So let's just see the solution. We have, so solution means it's solution to part A. Okay, n to the power 4 plus 4 is equal to n to the power 4 plus 4n square plus 4 minus 4n square. So we can of course write like this, and this, if you look carefully, is this 2 times n square times 2 plus 2 square minus 4n square. So this becomes the square of n square plus 2 minus, and of course 4n square can be written as the square of 2n. So that, if you use the usual formula, is factorized like this: n square plus 2 plus 2n times n square plus 2 minus 2n. So this is how we have expressed n to the power 4 plus 4 as a product of quadratic factors. Now this will be composite. From this factorization itself we can conclude that this is composite, provided that these integers are both greater than 1. They are positive integers, no doubt, but we have to show that they are both greater than 1. Now, since n is greater than 1, we have n square plus 2 plus 2n. Of course it's also greater than 1, because n itself is greater than 1. This will be even more, that is greater than that itself, greater than n itself, and so it's greater than 1. And what about this other thing, n square plus 2 minus 2n? Now this can be written as n square minus 2n plus 1 plus 1, and this is the square of n minus 1 plus 1. So because n is greater than 1, this is non-zero. This is non-zero means it will be positive because it's a square, and that too, yeah, that is enough. So that just simply tells us that this will be greater than, strictly greater than 1. So both of these factors are non-trivial factors of n to the power 4 plus 4. Hence, this is composite. Although looking at the number itself, it's not immediately apparent that it's composite, but it is. Okay, so let us next see part B. If n greater than 4 is composite, if n itself is a composite integer and is also at the same time greater than 4, then n divides n minus 1 factorial. We have to prove this. Okay, so let's see how we can prove this. Solution to this part, to part B. Since it's given that n is composite, so we can in the beginning itself assume a factorization of n as a product of two integers, two positive integers, where a and b are integers satisfying some inequalities. A and b are integers such that none of them is equal to 1 and also at the same time none of them is equal to n. If you just simply assume that none of them is equal to 1, if both of them are greater than 1, then none of them can be equal to n as well, okay, because their product is n, and of course one of them will be less than or equal to the other. We can assume without loss of generality that a is less than or equal to b, and this is strictly less than n. Okay, now two cases arise depending on whether a is equal to b or not equal to b. If a is strictly less than b, then both a and b appear in the expansion of n minus 1 factorial. Why though? That's because you see what type of numbers a and b are. Both of them are greater than 1, but at the same time they are both less than n, means they are less than or equal to n minus 1. So if you expand this, if you use the definition of n minus 1 factorial, what will you write? N minus 1 times n minus 2 times n minus 3 all the way up to 1, 3 to 1. So among those factors, both a and b will appear because of this, because of them being distinct and because of them satisfying these inequalities. So that means they will distinctly appear as factors in this product that n minus 1 factorial is. So that is why their product, that is AB, obviously will divide n minus 1 factorial, and that AB is n. So this divides n minus 1 factorial, and this is when a is less than b. So now assume that a is equal to b. i.e. n is a square, because n is ab, because a and b are equal, now n is a square. And there is something else also. So n is the square of some positive integer, but n has to be greater than 4. So what is the smallest square greater than 4? 9, because that is 3 square, that is the next square. Since 9 is the smallest possible value of n we have. So accordingly, the smallest possible value of a will be 3. So a will be greater than or equal to 3. And from this inequality, we can now say something. Thus, let us concentrate on this integer a times a minus 2. Well, because a is greater than or equal to 3, a minus 2 will be what? Greater than or equal to 1. So that means a times a minus 2 will be greater than or equal to 3 times 1. That means 3. So this is greater than or equal to 3. And 3 of course is strictly greater than 1. Okay. So this is one thing. And let me just see, I lost the train of thought. And from this, we can next conclude this, which implies n minus 1, that is a square minus 1. And this a square minus 1 will now be greater than 2a. But how is this coming? I mean, where is this coming from? It is coming from here. If you think of it here as a rough work, a times a minus 2 is greater than 1, right? This implies a square minus 2a is greater than 1. And now if you add 2a minus 1 on both sides of this inequality, you then get a square minus 1 greater than 2a. But a square is nothing but n, so n minus 1 is greater than 2a. And of course n minus 1 is also greater than a, okay, at the same time. Let's just mention that also. Also, obviously n minus 1 is greater than a. That's because 2a is greater than a. Okay, so now what have we found in this case? In this case, we see that both a and 2a will appear in the expansion of n minus 1 factorial. And since a is not equal to 0, a and 2a are distinct. Just like previously we had distinct a and b, here that role of b is being played by 2a. Okay. Hence, both a and 2a appear in the expansion of n minus 1 factorial. So their product will divide n minus 1 factorial, but we don't really need their product. We just need the product of a and a, which is a square, and that is n. So in particular, n also divides n minus 1 factorial. Thus, n, which is a square, divides the factorial of n minus 1. So in this case also n divides n minus 1 factorial. Okay, so that is the solution to part B. Next, part C. Any integer of the form 8 to the power n plus 1, where n is at least 1, that means n is a positive integer, must be composite. Here also the value n equal to 0 has been avoided, because in that case 8 to the power n plus 1 becomes 2, which is not composite, it's prime. Here, let me just complete the exercise first. Is composite. Here also there is a hint, and we are going to follow the hint, so I am not writing it separately. The hint just says that 2 to the power n plus 1, this integer divides this 8 to the power n plus 1, and that fact comes from a simple identity from elementary algebra. We are going to use that identity to factorize this. Solution. We have 8 to the power n plus 1 equal to the cube of 2 to the power n using the usual laws of exponents plus 1 cube. Now you apply that formula which factorizes a cube plus b cube from elementary algebra, and that thing is a plus b times a square minus ab plus b square, if you remember it. Minus ab, b is 1 here, plus b square, 1 square is 1. Okay, so now all we have to verify is that both of these factors are greater than 1 in order to conclude that this is a composite integer. Since n is at least 1, we have this will be greater than 1 even if n is 0, or in fact negative also, because any such power is a positive real number always from properties of exponents. But anyway, we have it greater than 1. And what about this one? There is a minus, but if you carefully take 2 to the power n common out from the first two terms, then you see that because the least value of n is 1, if you put 1 here, then this becomes 1. Okay, this 2 to the power n minus 1 becomes 1. It does not become negative. It becomes positive, and if you take higher values of n, then it will be even greater than 1. So in any case, this part is positive, so positive plus 1, this is also greater than 1. Thus, this integer is composite. And lastly, there is part D. each integer n greater than 11 can be written as a sum of two composite numbers. Here also we have elaborate hint. Instead of writing the hint, let me just write the solution itself. The solution is based on the hint. So we have to prove that any integer n that is greater than 11 can be written as a sum of two composite numbers. Note carefully that here we are not being asked to show that n itself is composite, but rather n is the sum of two composite numbers. So here the thing goes like this. Definitely this n is either even or odd. So let us consider the even case first. Let n be even. So n will be of this form. (2k) for some integer k. Now since n is greater than 11, we must have k greater than or equal to 6. That is the smallest value k can take, that is 6. Okay, it cannot go smaller than that, because otherwise n will become less than 11. Now our aim is to show that n can be written as a product of two composite as a sum of two composite integers. So now n can be written like this: 6 plus n minus 6, and 6 of course is itself composite, but what is n? N is 2k minus 6, and this second number is 2 times k minus 3. Note that six and 2 times k minus 3 are both composite. Six is composite, that's just a fixed concrete number, and we know that it's composite. Why is 2 times k minus 3 composite? That's because 2 is greater than 1. Already it's a factorization. Okay, now the question is this a non-trivial factorization? We see two factors, one of them is already greater than 1. But what about k minus 3? K minus 3 is also greater than 1. In fact, k minus 3 is greater than or equal to 3. So that's why are both composite. In brackets you can write since k minus 3 is at least 3, which is greater than 1. Next we consider the case where n is an odd integer. Let n be odd. All right. Then n minus 9 is even, right? N minus 9 will be even because n is odd and 9 is also odd, and the difference of two odd integers is an even integer. But at the same time, because of this inequality, n minus 9 is greater than 2 and greater than 2. Okay, now any even integer greater than 2 must be composite because the only even prime is 2. All the other even numbers are composite. So n minus 9 is composite. Yeah, now it's easy. Now you just write n as 9 plus n minus 9, where both 9 and n minus 9 are composite. So regardless of the parity of n, it does not matter whether n is even or odd. If n is greater than 11, then in each case you can express n as a sum of two composite integers. And this is where the solution finally ends. And let me just end this video here itself. There is no point dragging it longer than this. Our next upload is this coming Friday, and on Friday we will do graph theory again, where we will solve the subsequent problems, okay, the ones that come after what we have already solved in the previous graph theory video. So with that, I'm signing off for tonight. So see you on Friday with graph theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.